The ones that are not so easy to identify are the organic ones, the organic bases. And organic bases are also called Bronsted-Lowry bases. Or what I'll call them from now on, BL bases. Bronsted-Lowry bases are organic bases, and so they have to have carbon-hydrogen bonds. The example that I used in the script is this compound right here. This is known as methylamine. Now there's a whole branch in organic chemistry that deals with the amine compounds, which of course we're not going to spend very much time on, but there's tons of them out there. If you dissolve this in water, you get a pH greater than 7. And you say to yourself, well, what the heck? There's no hydroxide there. Well, there is one when you dissolve in water. Now, acids and bases become reactive in a strong sense, particularly when you dissolve in water. They aren't really acids and bases until they become dissolved in water. Then the name acid and bases comes out, because as already has shown, it was going to allow the hydrogen and the hydroxide ions to come out. This being a base, somehow hydroxide is going to come out even though there's no water, and that's because we're going to add water to this. Now, when we look at chemical reactions involving compounds like this, we are going to find out that water has a rather special quality to it. So let's look at the Lewis dot structure for water. And we talked about this in the last one as well, last lesson. And as we said before, we said that when this breaks apart, both electrons stay here. They don't go to the hydrogen ion. So that means then that this can be positive here, and this can be negative over here. And we showed that when we actually look at a true representation, or a truer representation, not a true representation, but a truer representation, with the bond angle being right around 109.5 degrees or 107 or whatever it is, we know because of the electronegativity of the oxygen grabbing these two electrons here, that we're going to get a positive charge for this, and the rest of the compound, which is known as hydroxide, is going to be negative. Now this bond can be fairly easily broken, but most of the time it kind of stays intact. Like I said, this only happens in every 1 out of 10 million molecules that actually breaks apart. So this is really difficult to do under normal circumstances. However, let's take a look at the Lewis dot structure of methylamine. Methylamine looks like this. And it's that pair of electrons that nitrogen has that causes this sensation to occur. So what we're going to do, instead of looking at it in terms of H2O, we're going to look at this in terms of HOH. And with the understanding that this is kind of positive, and when to designate that, we use a Greek letter delta right here. And there's capital delta, which is a triangle. But there's lowercase delta, which signifies the fact that this is a tiny positive charge, and this over here is a tiny negative charge. But it's the tiny positive charge right here that's going to be attracted to this pair of electrons. It really likes it. Opposites attracts, right? You're not sure? Check out the hallways sometime. There's a lot of attracting opposites walking those hallways. It's a natural phenomenon. Scary sometimes, but natural. So that means then that this hydrogen here is going to move over here. But like I said, only 1 out of 10 million molecules break apart, so the hydroxide is going to go with it. And so the resulting Lewis dot structure is going to look something like this. And it's going to form a single bond between the nitrogen and the hydrogen. Oops. with H and then OH. And now, ooh, look, there's an OH on the end of this thing. This is now a base. So we can rewrite this as CH3 for this part. This part has NH3. And then we have an OH stuck to that third hydrogen. And there is your Bronsted-Lowry base, or your organic base. And so we can treat that like the base we would for other compounds. So this is the thing that we're going to have to do in today's lesson, is to be able to come up with Bronsted-Lowry bases based upon the Arrhenius base. I'm sorry, that is not a Bronsted-Lowry base. I said that incorrectly. This is an Arrhenius base because now we have the hydroxide on it. My mistake. And this is a Bronsted-Lowry base right up here, because there is no OH. So you're going to take Bronsted-Lowry bases and change them to Arrhenius bases by adding HOH. And you'll notice that the number of hydrogens increased by 1, and then you put an OH on the end. So we had NH2, and then that became NH3 because of the first hydrogen, and then the hydroxide then follows. That's all there is to it. So, if I were to write this chemical reaction, I would have CH3, NH2, liquid, and I will give you the faces for these things, plus water, H2O, liquid, but again, think hydrogen hydroxide, and the resulting compound is CH3, NH3, OH, and that will be aqueous because it's basically dissolved in water. A few of the molecules will react to this, the rest of the water molecules will not. They'll just dissolve. All right? Practice problems. Because right here, we've got these compounds. Now, this is a single bond between the nitrogen and the carbon here, and this is a single bond between the nitrogen and the hydrogen here. So, have fun.